Hello, this will be a demonstration of Proposition 5 from Book 8 of Euclid's Elements, which says that plane numbers have to one another a ratio compounded of the ratios of their sides. Remember what plane numbers are? They're just products, basically. So like 6, that would be a plane number, and its sides would be 2 and 3. 16, that would also be a plane number because its sides are 4 and 4. It would also be a square number, but it is a plane number. So plane numbers, they're just products. What we want to prove is that they have the ratio compounded of the ratio of their sides, or what we would say now, they're factors. We're given two plane numbers, A and B. The sides of A will be C and D, and the sides of B will be E and F. What that means, in other words, is that C times D makes A, and E times F makes B. And what we want to prove is that the ratio of A to B is compounded of the ratios C to E and D to F. We're going to begin by creating three numbers G, H, and K, such that G is to H just as C is to E, and H is to K just as D is to F, and these will be the least numbers in such a continuous proportion according to the ratio C to E and D to F. We can, of course, create the three numbers G, H, and K by the previous proposition 8.4. And the final thing we're going to do is we're going to take the product of D and E, call that L. So D times E makes L. Now, because the number D has been multiplied by the two numbers C and E to make the two products A and L respectively, so remember D times C makes A and D times E makes L, we can say by proposition 7.17 that the numbers multiplied have the same ratio as the products, that is that C is to E just as A is to L. But you'll remember that G and H, we made them such that G is to H just as C is to E. So we have two ratios, which are the same with the same ratio property of numbers. They are the same as one another. So G is to H just as A is to L. Now we can go through a similar line of reasoning as just presented in the second and third step to prove that H is to K just as L is to B. Now, because G is to H just as A is to L, and H is to K just as L is to B, we can therefore say xi quali, going between the extremes through the mean, that G is to K just as A is to B. So we're skipping over the H, we're skipping over the L to put the extremes in a ratio with one another directly, so that we can say that G is to K just as A is to B. We can, of course, say this by proposition 7.14. But you'll remember that the ratio of G to K is compounded of the ratios G to H and H to K. That's just obvious. And we know that G is to H just as H is to K, or G is to H just as C is to E, and H is to K just as D is to F. So we can say that the ratio of G to K is compounded of the ratios C to E and D to F. Now, the ratio G to K being the same as the ratio A to B, we can also say this of the ratio A to B. That is that A is to B, or the ratio of A to B is compounded of the ratios C to E and D to F. And this is precisely what we set out to prove, which means we are done with the proposition, therefore, etc., Q, E, D. This is the second time we've seen compounded ratios. The first time we saw this idea presented was in proposition 6.23 about equiangular parallelograms having the ratio compounded of the ratio of their sides. This is a very similar idea, where instead of talking about equiangular parallelograms, we're talking about products, and instead of sides, well, we're still talking about sides, but sides here are numbers instead of lengths. You'll also remember from that proposition 6.23 that what is meant by compounded ratio is simply multiplication of ratios, or the product of two ratios. So what that would look like here is, say we have two numbers, 15 and 28. And what we want to say about this ratio right here, 15 to 28, is that it is equal, or not equal, the ratio 15 to 28 is compounded of the ratios of their sides. Well, the sides of 15 are 3 and 5, because 3 times 5 makes 15. And likewise, 28 is the sides of 28 are 4 and 7, because 4 times 7 makes 8. So what we can say about this proposition is that 3 to 4, the ratio of 3 to 4, compounded with the ratio of 5 to 7, or simply multiplying their ratios, is equal to the ratio of the original plane numbers, or their products. So we can just go straight across. 3 times 5 makes 15. We put that on one side, and 4 times 7 makes 28. We can put that on the other side. So yeah, if you've ever wondered why multiplying fractions is just that easy, you just multiply the numerators, multiply the denominators, and stick a bar between the two. If you ever wonder why it's that easy, this is why it's that easy. So that's all I've got to say about this proposition. So I'll end the video here and move on to proposition 8.6.